So good morning everyone. Let's continue the discussion on CoAP. Yesterday it was all introduction. Today we will see the message types, formats, etc. and how exactly packet loss is managed and such details. Okay, yesterday it was asked by one of your friend, how are we going to do with packet loss since it is using UDP. Okay, so CoAP messaging basics. So at the transport layer it uses mainly UDP. It means that it's possible to make CoAP to run on top of TCP, which most of the time we will not attempt because TCP will defeat the whole purpose of having a lighter protocol. Message exchange between the endpoints could be clients or servers or the devices. So you have 4-byte header shared by request and responses. So both request and response messages share the same type of header. It has a message ID, 16-bit message ID is there, which is used to identify the messages from one another. And reliable exchange, wherever you require, we go for confirmable messages. Okay, so we know that the transport layer has not given you any reliability. So you have to take care of that reliability part in terms of confirmable messages, for which you can expect an acknowledgement, or you can get a reset message. So simple stop and wait transmission with exponential backoff is used for triggering the retransmission in the case of a packet loss that we are seeing in detail today. Unreliable exchange is made through non-confirmable messages. So fundamentally there are two categories of messages: confirmable messages and non-confirmable messages. And confirmable messages are used when you expect reliability, and non-confirmable messages you just send the data and forget about it. And duplicate detection is happening through message ID, and message ID is going to be unique for every message that you are sending. So you can discard the messages with same message ID and operate. Now let us see the details how it goes. So in the case of a confirmed messages, you have what is known as CON and message ID, and you get a response. This message ID of the acknowledgement will be the same as that of your confirmation request. In the case of a non-confirmation, you just send the request and then go ahead, don't wait for that. So the requests and responses are piggybacked on COSP messages, REST requests. So REST requests will be there for accessing the contents from web pages and resources that are piggybacked. And this is how it looks like. Your application is there. Application gives you CoAP request response messages, and then it runs on top of UDP. Okay, so let's see request response examples. In the case of confirmed, this part is talking about confirmed. You are sending confirmed a message ID and get temperature. You are issuing a message token also, and the response comes as an acknowledgement, and the data is also coming back. It's a piggybacked acknowledgement with the data. So you have the same message ID. You can relate the acknowledgement to the request and then the data, talk 22.5C, and the token is also there. Okay. Next, if it is happening in the case of a this is also again, if the resource is not ready, if your temperature sensor is not set up properly, you reply saying that the data is not found. Now earlier we found the case with a piggybacked response. Now it's possible to have a separate response. That means you don't load anything on top of acknowledgement, let the acknowledgement go freely. After that you send the data. Okay, so you have connection, temperature, and the acknowledgement is obtained. After some time, the data may not be ready at that time or some issues. After some time, when the data is ready, the server responds with the data. Okay, so you can relate these two messages by means of the connection So not connection, token ID 0x7373 is coming here. Okay, so that is how it works. So again, the client acknowledges with 23BB. Okay, because it was a connection that is coming from server to the client, so it is acknowledged with the same ID, message ID of 23BB. So this is how it happens. So you will find lot of similarity between the way TCP works. Okay, so a protocol at the application layer is mimicking the way TCP works. So what is the conclusion? Yeah, this protocol is taking care of reliability at the application layer. Okay. Non-conformable is nothing here. You send non, then you will not get any acknowledgement. Okay, now the message header. See, this is the main attraction, 4-byte header. Okay, so you have got only 4-byte header version. The details are here. Spend some time here and understand the details. And we have learned this for many other protocols earlier, isn't it? Some of you may be able to recollect it. IP header format, TCP header format, UDP header format, etc. Likewise, it's good if you can relate the header fields to the ones which you have already learned, so that you can easily understand. Okay, so I won't ask you to study it because this is already studied under different names. Now all that you have to do is just a mapping from this CoAP to the things that you have already studied. Option format. The option part is optional and you can give a lot of options and it works in different ways. This is similar to different levels of services which we give in IP. Okay, length, things like that. This level of details are not required for us. As I always say, even without completely ignorant about this, you can do CoAP applications. That's the beauty of computer science. Okay, now as some of you asked yesterday, how are you going to deal with packet loss in the application layer? So a packet is lost, it's not reaching as a server, so after a timeout you resend it. Okay, and acknowledgement is, then what will happen if acknowledgement is lost, etc. Such questions are coming, we will address them now. So a stop and wait approach is used. You send a confirmable request and wait for a definite amount of time till that acknowledgement is arriving back within the timeout interval. You trigger a retransmission. Okay, so you need to get some acknowledgement, isn't it? So initial timeout is set to a random value between these intervals. Okay. So this two interval is ACK timeout and ACK timeout multiplied by a random factor. It's going to be between 2 seconds and 3 seconds. I also do not know the actual details. So there is a well-defined method for setting the timeout. It's not somebody tossing a die and selecting the time. So when timeout expires, what can be done? The retransmission counter is less than max retransmission. That means if you have not reached the maximum retransmission attempt, you can do a retransmission. And then as we do in TCP, increase the transmission counter, because this timeout is an indication of the network behavior. If the network is heavily congested, you cannot expect the acknowledgement with the previous timeout. You need to increase the timeout. And the increase can be a double in the timeout value or some value. It all depends on the specific algorithm that you are using. Okay, so in this procedure, that is retransmit, increase the counter, retransmit, increase the counter. How long it will go? It will be done until you hit the maximum retransmit count. Okay, so within this, two things can happen. You will get an ACK, or an RST is received, or you exceed the maximum retransmit. Okay, so the total if total attempt duration exceeds max max retransmit wait 93 seconds, then you need not worry much about that message, because that message has become useless in IoT scenario. Okay, so we need sensor data. within stipulated amount of server. So most of the time we will not hit this worst scenario. Everything happens before that. So if you are curious about it, you can simulate it. I'll tell you the tools for simulation at the end of this lecture, but it requires some self-exploration. I don't know how far you can go in that direction, because you are loaded with placement projects in all courses. So I do understand your limitations in exploring it further. So I'm just giving you the topics and leaving all it to you, and you can take the decision. Okay. Now, next thing is, let's see the proxying that happens in the CoAP world. So as usual, the proxy is somebody who sits in between the actual resources and the person who accesses it. Let's say there is an HTTP client talking to a proxy for getting the light temperature. So if it is data is, so the proxy talks to the CoAP server on behalf of the HTTP client. So here the proxy is talking to CoAP, not to the HTTP. That also you need to know. So it gets the data and caches here and responds back to the client. Next, again a request for light comes. He looks at the cache. If the cache data is fresh, and we have learned how to check whether the cache data is fresh or not. Okay, there are some fields in the header, time last modified, etc. Based on that, you determine whether the cache data is fresh or not. If it is fresh, you deliver it to the client. That's all. Otherwise, you have to initiate again connection to the server and get the data. Okay. Now some fundamental issues with the REST. So REST is actually pull mechanism. That is, the clients are always pulling. That is, they need not request all the time. They will keep on getting the data. How do we bring in that technique into the CoAP? And this is the pull method is, and another thing is the data in WSN. If you use wireless sensor, you have a WSN setup, and WSN have periodic data. How do you take care of this periodicity of data with CoAP? So that's also done here. That is known as observation parameter. So you have what is known as an observe register. So you send a client will send a request with an observe register. Okay. Registration with the server. So the server notes down that client has requested for an observation. It has registered by setting the option field as register. So he has registered for temperature. So whenever there is a state change in temperature value, the client will be getting messages. Okay, so notification on the client state. So this is obtained. So you can spend some time on this slide and understand how this is working. Now next thing is, if you are operating at IPv6, IPv6 fragmentation is different from that of IPv6, IPv4. We will look at it later, and it's already learned. IPv6 requires a minimum segment length of 1280 bytes in its payload. If your data is not making up to 1280 bytes, you can combine different CoAP messages and make a block and then put into the segments of the IPv6. Okay, so that's what happening here. You combine everything into a single IPv6 and make up together. Okay. So block 2 option is added if you are going for block level transfer. Okay, the entire stuff is carried out in one network layer message. Okay. So resource discovery. How do we find out the resource available on the internet? We have got CORE, Constrained Resource Discovery Protocol. It send the message and get the responses. Okay, so getting started with implementation. So I would suggest you to go with Contiki simulator. It's actually a virtual machine VMware kind of setup, and all other libraries are there to support you with the CoAP. Okay, so we will have a demonstration of CoAP maybe in the next lab session or theory session. In the meantime, you can explore it and find out how CoAP can be used in your use case.